So now that we have our definition, right, of the definite integral, we're going to look at some examples. And before we do that, I want to look at some properties of this definite integral that are going to help us out, right, when we start getting specific. And a lot of these, I think, are really kind of intuitive. This first one, for example, we had the exact same property when we talked about derivatives, and we had the exact same property when we talked about limits. If you have a constant, you can bring that constant out front and then do the integral part, right? And this follows from everything we've talked about so far. This first integral, that's the limit of the sum of k times f of x. But we have a property of finite sums that says I can bring that k out in front here. And then we have a property of limits that says I can bring the k out in front of the limit. We're left with this, which is just k times the integral of f of x. And this next one, same kind of argument, right? The left-hand side is the limit of the sum of f plus g. Well, we have a limit. We have a property of finite sums that says this is the sum of the individual functions, and then we have a property of limits that says I can split it up to be the sum of the limits. This right-hand one is this definite integral. The left-hand one is this definite integral. Kind of properties we'd expect to have. Now, this third one is a little more interesting. What if I integrate from a to a? Now, let's think about this, right? This is the limit of the sum of f of x times delta x. But what's delta x? The width of our interval from a to a is 0. That means that delta x is going to be 0. So this is the limit, the sum of f of x times 0, which is the limit of 0, which is just 0. Yeah? Okay, so this next one, this kind of goes back to what I was saying about the finite number of discontinuities. This is saying, look, if I have this interval from a to b, and there is some point c here in the middle, then if I find the area of this part and add to that the area of this part, I get the area of the whole thing. Right? We can do this is the classic geometry trick. If you don't have a formula for the area of something, split it up into pieces that you can find the areas of and add up the parts. Okay, now this next one is a little more interesting. This one is saying if I reverse the order of the limits, instead of going from a to b, I go from b to a. See what our formula, our property is saying here is that changes the sign of the limit of the integral. Right? Well, I need to make a little room here. Originally, right, when we're going from b to a, delta x is b minus a divided by n. But how about if I go the other way? If I go the other way, then delta x equals a minus b divided by n. But this is equal to negative b minus a. So you see all of our delta x's change sign. And since every term in the sum is being multiplied by a delta x, that just reverses the sign of every term in the sum. Okay, bunch of properties. Now I have a couple more here that are maybe a little more interesting. Okay, the first one is saying, let's say I have my function and it's going along here doing what it does. You notice I kept it all positive, right? What this is saying is if I'm integrating from a to b, this area, and we have to do a couple colors here, the area under the curve, that's the definite integral in the middle, is greater than the minimum of f times b minus a. Well, look, the minimum of f is here. The minimum of f times the length of the interval, that's this area. And yeah, you can see that is less than the area under the curve because the area under the curve has those two extra pieces up on top. And this other side is saying, look, suppose we look at the maximum. That's this point here. Well, the maximum times b minus a is this area. Yeah, that's going to be bigger than the area under the curve. All right, and finally, this second property here, this one says, look, suppose we have two functions, and one of them is always bigger than the other. So this one is f, and this one is g. If f is always bigger than g, then the area under f is going to be greater than the area under g. Okay, again, bunch of properties. Right, let's see how we can use some of this stuff. All right, so what I want to do is I want to evaluate this definite integral. Remember the only way we have to interpret this definite integral is this is the area under f of x equals x, that's the function here, right, from 0 to 4. Okay, well, let's see what that looks like. Right, I'm going to draw f of x equals x, and I want the area under this curve from 0 over to 4. Okay, so that's this area here. Okay, well, wait a minute. I know that, right? That's a triangle. The base is 4. The height is, whoops, not h. The height is 4. So the area is 1/2 the base times the height, which is 8. So that's my answer. That's what this area, that's what this definite integral equals. Right? You see, I'm using a very geometric interpretation, right, to answer these questions. Okay, so how about this one? Go ahead and think about this one for a minute. Right, see if you can't think this through, come up with the answer. Well, what is our function? This is the area under f of x equals 1 from -3 to 5. So let's do what I did the last time. Let's graph this. F of x equals 1 is this horizontal line. And I want to go from -3 out to 1, 2, 3, 4, 5. So I want the area of this shape. But again, I know what that is. It's a rectangle. The area of a rectangle is width times height. The width of this thing is 8. The height is 1. So that's the area, and that is what my definite integral equals. All right, try this. Let me let you try this one as well. Try this one, see what you come up with. Okay, y equals x plus 3. Well, that's a line, right? Its y-intercept is 3, and its slope is 1. So it's going like this, and it continues on this way. And I want to go from 0 over to 2. So that is this figure here, right? I want that area. Well, what shape is this? To see this, you might need to turn your head sideways, right? Rotate this a little bit. That's a trapezoid, right? It's kind of a trapezoid that's rotated 90 degrees. So the bases are going, the vertical sides are the bases instead of the horizontal sides, right? But I can see this base here is 3 units. Let me do it different color. This base is 3 units. The other base is 5 units. And the height here is 2. You remember the formula, the area of a trapezoid is 1/2 the sum of the bases times the height. So this is 1/2 3 plus 5 times 2, which is 8. So that's it. That's my definite integral. Another way you could have approached this, if you didn't remember the formula, right, for the area of a trapezoid, you could have come over here and again used that geometry technique, split this up into 2 parts. I split it here, found the area of this triangle, added to that the area of this rectangle. You got the same result either way. Okay, so how about this one? I want to use this inequality. The sine of x is less than or equal to x for when x is greater than or equal to 0, to find an upper bound for this integral. So how am I going to do this? Well, I'm going to rely on one of those properties we had a few slides back, right? Remember, we had a property that said if f of x is less than or equal to g of x, then the integral from a to b of f of x is less than or equal to the integral from a to b of g of x. Well, here, sine x is f, and x is g, and my limits are over here in the integral. It's from 0 to 1. Right, so let's just drop this stuff in here. The integral from 0 to 1 of the sine of x is less than or equal to the integral from 0 to 1 of x dx. I left the dx there. There we go. So the integral from 0 to 1 sine of x dx is less than or equal to, so what's this going to be? Well, that's triangle again. Right? There's f of x equals x. We're going to go from 0 out to 1. So this distance is 1. The height here is 1, which means the area of this rectangle equals 1/2 1 times 1, which is 1/2. And there's my upper bound, right? The upper bound on this area, the upper bound of the area under the graphs f of x equals the sine of x from 0 to 1 is 1/2. Now, that's nice, and sometimes that's all we want, right? Sometimes all we want is an upper bound. But it would be nice if I could get exact answers for any integrable function, right? So far, I've limited myself, right? We talk about what's coming up next, right? So far, I've limited myself to talking about functions that give me nice geometric shapes, right? That I have classical geometry formulas for. What if we have something like the sine of x, where I don't? Okay, well then what can we do? Okay, that's what we're going to talk about in the next lecture. This really brings us to the highlight, to one of the real highlights of the class. We're going to talk about something called the fundamental theorem of calculus, which is going to answer that question. It's going to give us a way to find the area under a curve, really relatively easily using the antiderivatives that we talked about back at the beginning of this chapter.